of fun stuff happening in the BPF space. So Red Canary has introduced Oxide BPF, a new Rust library for managing eBPF programs. It has one end goal, which is write once and run almost everywhere. This is by Rafael Ortiz. We've seen him speak at eBPF Summit and some of the other ones. So this is a fully BSD3 licensed library. I haven't explored exactly what's in here, but it looks like, it's always great to see new libraries showing up and stuff like that. So if you've been playing with Rust or if you've been exploring it, now it looks like there's another good option here for a library. Check it out. Also, I wanted to share, in case you had not seen it, we have revamped the Cilium.io website. And if you go to the Cilium.io website, down underneath Discover Cilium, you'll see a weekly interactive session with Thomas Graff. And then you'll also see the weekly community install fest. So if you're interested in joining us and just going through the process of installing and exploring Cilium, that will be available to you. And then we also have a number of do-it-yourself tutorials if you just want to play with this stuff. So definitely come hang out and explore this stuff with us. And yeah, it's gonna be fun. What else do we have? All right, I think I'm going to introduce Martynas. Let me get Martynas in here with me. How you doing, Martynas?
Hello, all good, all good. Calling you from snowy Europe.
Yeah. Oh, is it snowing where you are?
Yes, actually. Yeah,
nice.
Winter is here. Super excited.
Yeah, I bet. Has it been? Is it like just kicking off like the snow season, or has it been snowing for a little while now?
Yeah, it just started. So actually, I live quite high in the mountains. So yeah, summer and autumn is over. So
nice.
Looking forward to snowy months.
Yeah, awesome. Well, Martynas works with me here at Isovalent. And do you want to introduce yourself?
Yeah, so it's my second time when I'm on the show. Like last time presented Wirecard. And today I would like to talk about this PWRU debugging tool. So yeah, shortly I'm Martynas, working at Isovalent as a software engineer, like working on the Cilium data path. Although my title says software engineer, so I think you might imply that I'm writing software most of the time, but actually most of the time I'm actually debugging. Yeah, majority of time is spent debugging networking issues.
Big mood, yeah.
Yeah.
So. I suspect that's probably true of a lot of people who are writing software. I know that's. I mean, I consider myself an engineer, but more in the infrastructure space, and I spend almost, at least 80% of my time debugging or understanding the state rather than actually making significant change for. Yeah.
Yeah. So basically, the tool which we're gonna talk today came as a side project to facilitate the debugging. Yeah, so before actually joining Cilium and Isovalent, I've been working at Weaveworks on WeaveNet, another CNI plugin for Kubernetes, and yeah, I have quite decent experience debugging Kubernetes networking issues. So basically, this brought me to this tool, like writing this tool and publishing it to the wider audience. So hopefully it will help you to catch all the Heisenberg bugs and like difficult to catch kernel bugs, etc. So
makes sense. Oh, cool! I'll throw up a link to the repository. Like usual, if you are attending this session down here in the lower down there, where it says show notes, you can go to hackmd.io/echo-live, and you're going to find a published set of notes for each of the episodes that we've done as part of the Echo live stream. And this one is episode 28. So if you click on that, you're going to find all of our notes, and that link our notes there will take you to a recording of a KubeCon talk that Aditi and Martynas just recently delivered at KubeCon Los Angeles, and also a link to the repository where the code for PWRU is hosted. So yeah, do you want to share your desktop and kind of explore this with me, or?
Yeah, So maybe I could. Okay, so maybe I'll start with a short history, and then we can dive into demo and internals of it. So yeah, basically back in the days of VFnet, I've been chasing different bugs, and back then, like a lot of infrastructure was relying on IP tables. So the natural tool for this was basically to build some kind of diff tool which could inspect the IP tables counters.
Yeah.
But then with the kubeproxy and also kubelet, like periodically refreshing the IP tables rules, it was resetting the counter, so it was very like non-productive way to debug the issues. And then I was actually reading LWN, which stands for Linux Weekly Newsletter. Maybe I should start sharing my screen. So I discovered like BPF. So back then it was just some small feature in the kernel, and I didn't see in the beginning like that it might be widely adopted as it is now.
Mm-hmm.
And I was still like in this, IP tables world, debugging those issues. And then I think Thomas from Isovalent, Thomas Graf, published this article, which basically said that kernel community is basically replacing IP tables and that BPF is the future. So this was kind of mind-opening article, basically predicting us how the future will look like. And it was written in 2018 and we are 2021, and like lots of predictions are actually true. So it was quite nice to read back then this article. So basically the idea was that the data plane will be moved from IP tables to BPF. So then it kind of opened my curiosity and I started actually looking into BPF. And then I thought like, okay, so with the BPF, we can do lots of random stuff. Like we can inspect the kernel state, we can forward packets, so we can do tracing, networking, etc. So maybe if like we could somehow see what kernel is doing with the packets, maybe it could help me to debug some kernel issues like customers are facing. And back then, I think the tool was BCC, like to write the BPF code. And I think it's still like people are using nowadays, but I found it quite heavyweight tool to write BPF programs because it requires you to ship together with the LLVM toolchain. So it kind of was no-go in some environment, customer environment. So yeah, so just to rewind, basically, I was looking into a tracing program, which could tell me like what kernel is doing with some particular packet. And when I say particular packet, I mean like, okay, so this is the IP address, this is the source port, this is the destination port, this is the L4 protocol. So I'm interested in the particular packet. And
I like that. Yeah, it's definitely one of the powers of eBPF that I think people like kind of first latch onto is the idea of context, right? Being able to actually know more about what's happening. Just the reporting functionality alone is already pretty cool.
Yeah. And then later on, I think the BPF trace appeared, but basically it still was lacking this filtering functionality. And I remember when I was interviewing actually for Isovalent, I had the interview with Daniel, with my colleague, and he is the eBPF co-maintainer. So actually during the interview, it was a good chance back then to ask him for all the BPF knowledge. So nice. I was asking whether actually there are some limitations to how many like K probes we can attach to the kernel. Are there like significant performance benefits, drawbacks, etc.? And he said like none. And then like he planted this idea to basically that we can attach K probes to all functions which are processing the packets. But back then it was kind of difficult because first it was not so trivial to retrieve the list of functions which are processing the packets. because back then there was no BTF, so you had to rely on the debug symbols. And usually in production, nobody was shipping kernels with debug symbols enabled, because it had a significant overhead in terms of storage. And then I was messing with the BCC, so I had like some scripts where I had the predefined list of kernel functions, etc. And then, like later on, I discussed with some colleagues that maybe with the existing infrastructure, we could actually write a tool which would parse all the kernel functions from the BTF, which is a debug format, a very compact format to expose the debug symbols in the kernel. And then from that, we could extract the functions which accept the SKB buff. So skbuff, which is the representation of the packet in the Linux kernel. And then we could attach a kprobe, which does some filtering and outputs if a filter is passing.
Because you have a mechanism for actually enumerating those functions that would affect the packet at this point.
Yeah, exactly.
You're no longer trying to figure it out from scratch. You actually have a place to start.
Yeah, and basically because this BTF is super compact, I think it's like 10 of megabytes or something on my kernel with lots of things being enabled.
Yeah.
So it's being shipped nowadays with all kernels. Like if you enable it, and I think majority of mainstream distros do it by default nowadays. So with this we could actually get the list of the functions. Then now is once we have those functions, we want to attach some programs, PPF programs to those functions, which do the filtering. So this brings me to another project, which is the Cilium eBPF library. So this is the Go library to interact with BPF infrastructure in the kernel. So this library actually allows us to write BPF, like to interact with the BPF in the kernel in relatively a straightforward way. So later on I will show some internals. So anyway, so once we have those two things, then writing this packet tracer in the kernel became relatively simple. So so I guess we didn't introduce or maybe we introduced the repo, but anyway, so this is basically the project, and it consists of two things, like Go, which is the user agent, let's say, and then we have a BPF part, which is basically the kprobes. So, and if you check, it has just 300, almost 400 lines of code. And then if I actually check how many, I think this guy should tell me. So how many lines of Go I have? It's just 157. So it basically shows that to do a fairly complex thing with the Cilium eBPF library is very simple. So
I have a question actually. Like while we're right in this context, if you're okay with it, like one of the questions I've been wrapping my head around this is like we've talked a little bit about like the BTF stuff that's hosted in syskernel BTF VM Linux or whatever, where like all of those symbols are made available, and we talked a bit about core, like the ability to compile once and run in a bunch of other places. What I'm trying to map in my head is that like clearly the BTF, like it seems like the core piece of it would be that you're effectively assuming that map will be available on those systems that you want to run this code on, right? And that what you're compiling is basically a reference to what you can derive from that map in each of those systems. Is that right? So like when you're describing a function that it's going, like if you're going to write a kprobe against a particular function, you're giving it a name. You're writing that against like the name of that function, and then your BPF, your Go library is basically going to use the map in syskernel BTF VM Linux to determine like which actual function by integer that is.
So it's close, but I think I should add a bit more.
I want to hear it. Yeah, like this is a question I've been trying to get to the bottom of for some time now.
Okay, so let's jump to the kernel source code. Let's say let's take IP. I don't know, output, let's say. Yeah, that's the simple. And if we check for SKB buff, let's say that okay, so maybe, okay, so let's say we have this function, IP local out.
Yeah.
And this function is accepting 3 parameters. So it's a network namespace, the socket, and then finally this SK buff, which is the representation of the packet in the kernel.
Yep.
So from the BTF, I can derive that IP local _ IP local out function is accepting 3 parameters, and the third parameter is SK buff. So what it means that what it gives to us, it gives us that the third parameter is SKB buff, and we know that this is the function name. So what we can do, we actually can attach the kprobe, which assumes that the third parameter of the function is the SKB. So that's why we actually have 5 kprobes, and it's actually taking the parameter from the third register, like if you follow the API conventions, and then it's passing to this function, which is doing everything. So like filtering and outputting. So basically, just to recap, you have a list of functions, and then you're interested in the position of the SKB parameter. And depending on the position, you attach the kprobe.
And is it, I mean, would it be materially different between the builds of a kernel? Or would they be effectively the same?
Some things might change, actually, but I would say 80% might probably not. In which we 80% of functions which are really interesting to us probably will not change the.
Okay, so the assumption when you compile this and you have you're basically in your compiled code making the assumption that the position the position of that argument for that function will remain the same, and this is the run everywhere part, right? It's as long as that continues to be true, then that will be true. Or is your code, when being evaluated on that destination system, using that map to validate that that's still true?
Okay, so then let me show one thing.
Okay,
I think this will make it clear to the audience. Okay, so this is the main Go program.
Yep.
And we are using this BPF to Go feature from the Cilium eBPF.
Yep.
So basically this allows us to, when you build a binary executable, you actually tell the Go generate to compile the kprobe source code and to embed it into the Go files. So basically this becomes available from the Go, and then you can actually interact with the through the Cilium eBPF library with those BPF objects. So with the BAPs, with the programs, for instance, I'm referencing here the kprobe SKB1, so the one which accepts the SKB as the first parameter. So basically, once we compile the program, this program has so-called those compile once, run everywhere relocations.
Got it.
So if I go back and open, we should be able to see those BPF core read. So this means that basically this binary is compiled. So let's say I'm compiling it on my machine and I'm passing you the binary, statically linked binary, so you can run it on your machine. So if your kernel supports the recent enough, which supports those core relocations, then you'll be able to run this program without actually needing to recompile it.
That makes a lot more sense. Thank you for that.
Yeah, and it's super portable, because if you want to run this debugger, you don't need to ship the LLVM line, etc. So you just ship 10 megs statically linked binary, and you can run it in a Docker container on Kubernetes cluster, etc. So
nice.
So this makes portability easy. So actually, it's fairly simple program, and again, thanks to the BPF kernel developers, which made it possible, the usability of BPF in general, like user experience, in my opinion, if we look, I know in the last 2 years, it has improved dramatically. And also, for instance, if I want to write some BPF programs and then to manage them, etc., like such things as Silumi BPF makes it so easy to do that. Again, thanks to the Silumi BPF developers, like the ones who are maintaining the library and fixing and adding features. So, yeah, I guess we dived a bit too much.
We did,
into
yeah, we did. But I learned a lot, and I think I think it helps answer a question that I know I've actually been asked a few times.
And basically, yeah, maybe this slide could illustrate how it actually works, but maybe it makes sense to show some demo.
Sure.
Before we check some internals. Okay, so that was the kernel. Okay, so let's say that, okay, so I'm going to run the PWR, although my colleague Joe suggested to pronounce it as Peru, so it's easier to pronounce, but anyway, so I'm going to attach those K-probes. It's currently quite slow on my machine, and the attaching time should improve once we're gonna have this new feature for attaching multiple K-probes at the same time. And it has been presented this year at Linux Plumbers conference. And yeah, so let's say that I will add the rule which is going to drop the packets, the TCP packets to the destination 1.1.1.1, which is the Cloudflare's DNS server. And let's check how the output actually looks like. Okay, please bear with me. And do I have, okay. Okay, so, let's wait a sec. So currently it's actually, I didn't specify any filter for functions. So it's actually attaching to all functions on my currently running kernel. So, and there's a way actually to filter which functions you want to attach, which significantly reduces the load time. And so, okay, so I'm going to run the curl, and I'm expecting that it will not work because we see here that we see the packet being outputted from a local process. And yeah, remember we discussed about this IP __IP local out function. So we see the output of it here. And then we see like this NF hook slow happened. And then the next function which got executed is K3 SKB. So in the kernel, when we see that K3 SKB has been executed, it means that the packet has been dropped. And usually the culprit of it is the, let's say, function above it. So in this, it's the net filter hook. And I didn't attach to the particular net filter module, which could provide a bit more context to a person, but this basically gives a good indicator or hint that the net filter is responsible for dropping the packet.
Nice.
And if I actually, remove this rule, let's see how the output looks like. Okay, so, okay. Do I have more? Okay, yeah. Okay, so there we go. So we got more stuff happening. And this is quite simplified view. I actually have a bit more complicated. So basically, if you look into the help function, so I was using output tuple just to output the tuple. So basically L4 a tuple with L3 address. But I can actually output a bit more. So for instance, I can output the stack, which is helpful when you specify the filters. So for instance, let's wait until I have completely detached all the K-probes, but do I have something? Yeah. So let's say output SKB and output stack. And I'm using this filtering function, which basically says that please attach the K probes to a functions which end with SKB. So K3 SKB gets into the is being matched by this regex. Okay, I think I can attach. So you can see now it's attaching just to 68 functions, and if I do curl, I get a bit more information. So in this case, I'm actually printing two things. So the SKB and the stack. So for instance, for the consume SKB, the stack trace is the following. So we can see which functions were invoked. So basically you have a stack trace. So we can see what led to this consume SKB. And then I specified output SKB, which I find super useful personally for debugging the kernel stuff and kernel bugs as well. So basically it prints me the completely output of this SKB buff struct with all the internal fields. And
I love this. This is like, when I think one of the biggest challenges I had whenever learning to code or working with code, one of the biggest challenges I always had was like in actually putting into my brain like the structure of the data that I'm working with, right? Yeah. Especially if I didn't write the structure, right? Like if I'm coming to the program later to make some changes and like mapping, like, okay, but what does it actually look like? And so I'm notorious for putting print statements into stuff, or I was a big fan of IPython, because IPython would like basically allow you to do a REPL-like thing where you could actually look at the structure of the data at any point and then understand exactly what it looks like while you're trying to figure out like how to change the thing you're changing. Yeah. And I love this because it is exactly that. Like you're actually able to see the structure of that packet, right? Yeah. And very cool.
And for us, it's super useful. I find it because, like, for instance, like getting a mark, or like, like checksum information, because we see quite a few bugs with the wrong checksum calculation and packets being dropped because of that. So currently, actually, I'm working at providing the same information for the return values, because sometimes it would be interesting to see like error codes the functions return, and also adding basically functionality to allow us to dynamically specify which fields to print. So that would reduce the output.
Like filtering on the
fields.
Information.
Yeah. So that's two things like which should come in the next version of this tool.
I like that it's relatively structured output though. Like it's like right now looks like it's structured, but it's not JSON, is it?
No. So I think we could add the JSON output to make it more,
that would basically
helpful
make it
for machines to parse.
Yeah, exactly.
Yeah, but right now it's like at least I'm using this tool more like on this, on the single node, and I'm parsing it with my eyes. So but definitely it's possible to do that.
Yeah, I was thinking of like enabling the whole like field of, because I know that like a lot of folks out there are pretty big fans of like JQ and that sort of stuff for like filtering structured data. Like this one.
Yeah, that's a good point. Yeah, actually, I didn't think about like JQ in this scenario. Yeah, but that would be nice. Cool. And so basically that's the tool. And if you check the source code, it's super simple. And actually, at the time, I knew that there's another tool, which is IPF Trace by Utaro. And I was thinking it has similar idea, basically attaching to the K-probes, but different filtering method. And also, the main hurdle is that it's written in C, and extending this tool is a bit of, would be a bit tricky, at least for me. So we ended up building separate tool, although we knew about the existing of this tool. So just wanted to give acknowledgements to Utaro, who worked on it. And yeah, so basically the internals of this PWRU tool is, as we saw, like we are passing some filter information, then we start this go process, and then that go process is retrieving the BTF information from the running kernel. So it's basically syskernel BTF VM Linux, and then parses all the functions, filters all the functions, try to find the ones which accept SKB, and then attaches the kprobes to it. And then those functions, if the filter is matching, then those functions are basically pushing some information to the perf ring buffer, from which this tool is also reading all the notifications. And the configuration of the filter parameters and also output parameters are stored in the BPF map. So basically, those kprobes are reading the map. So like this perf ring buffer and the BPF map are like two ways how you can communicate with the BPF programs from the user space. Basically, it allows us to have a shared state between those.
Yep. It's interesting that the configuration is held in a map. I like that. Yeah,
and actually, it's then it's just a single lookup, and the kprobes are reading that information. So yeah, if I have it, so it should do the BPF map lookup. So it's reading from this config map, and basically then it does the filtering. And it's relatively simple, as I mentioned before.
I do like the idea of being able to filter by that, though, because like as you said, both it loads faster and also like you can zoom in on just those things that you're actually interested in understanding better.
Mm-hmm. Yeah, and so it's a relatively new tool, and actually it's nice to see that people started to use it in the wild. So actually helping to debug some kernel issues. So so the plan is right now to release the 0.0.3 version with the kretprobe support, so that we could get some information about the kernel function return values. But basically, I think, like, when I think about the future, like if we come back to this article by Thomas about kernel community replacing IP tables with BPF, or like, let's rephrase, Kubernetes moving from the traditional networking like to eBPF based networking, which Cilium provides today, like data path planes. And then like if you think like about some recent development in the Cilium, like in the Cilium data path, for instance, if we take this virtual Ethernet device optimization with the eBPF, like we kind of see this not a trend, but like movement towards the direction that in the Cilium we try to bypass as much as possible of the kernel functionality. So we basically re-implement some things in the BPF, and just don't want to repeat myself, but we have like discussed probably in the past and in the past episodes of the show about the benefits of why it makes sense to write the BPF the networking data path in BPF. And basically with Cilium, like we're trying to bypass this functionality. So in the ideal world, we probably such tool shouldn't exist at all, because in the Cilium data path we provide enough observability points, which, for instance, can be consumed by the Cilium Hubble project, which should provide you enough context to debug the networking issues on your own. But still, I mean, we still see like people like relying on IP tables, so we're not in this ideal world. Although I think in 2019, I already demonstrated at KubeCon North America in my talk about Cilium's kubeproxy replacement, that even today, like back then, you could run the Kubernetes cluster with the net filter completely compiled out, like without any IP tables rules, like completely relying on Cilium providing all this functionality. So yeah, my prediction, like in a couple of 2 years, we'll see more such setups running.
Yeah, I agree with that. I've definitely seen it out in the field. And one of the things also that I think really resonates with me is like when you think about like what IP tables was originally developed for, like the scope of work that it was originally developed for was never something that included so much churn, to your point, right? Like having so many different things, configuring it so dynamically all of the time. That was never in the idea of the design, right? Like, like the idea was that you would define what those rules were and then live within the means of those rules. You wouldn't like change them constantly. That wasn't a thing. And that's why I remember being very surprised when learning that like in IP tables, the way that it's implemented, if you make a change to a rule, the entire set is then reloaded. Just one rule. There's no atomicity to it, right? And this is, I think, where like, one of those things where in BPF, I don't think people have actually like really internalized this yet, but with BPF, you do get that atomicity, right? When you want to make a change, when you make a change to that BPF program, you're making a change to that BPF program, one of a many in a chain that might be related to the way that we manage that traffic. But it's just, it's an atomic change, right? And that's actually the killer. That's the killer difference for me, right? Like looking at those two, understanding that we can, for example, implement a mechanism that says, if I want to grant a given process access to particular syscalls. And since we're sitting right there at that kernel interface, I can define the program that allows those syscalls for that program, like dynamically at any point. I could wait for the inrush of the program startup to happen and then apply a filter that allows for only those system calls that I know that program will need. Right? It's like thinking about the world of seccomp in a completely different way,
like if you check, like if you look into how workloads, let's say, looked 10 years or 20 years ago and how it looks like today, like
hugely
you have like a single host, like running multiple like different containers, like short-lived containers, like you are no longer able to rely on IP address. And I think the crucial thing in the IP tables world is still like identifying the workload by the IP address, which is cannot be held true anymore in the Kubernetes environments.
Yeah, true statement. Well, awesome. Well, thank you for the demonstration and all of the information on PWRU. I can see that it's very helpful, and I actually really liked the view of that data structure, because like it's definitely one of those things where like I feel like that was always the hardest part for me to wrap my head around. I'm not sure about the audience, but it was like, for me, it was like, I always want to see, like, if I'm going to make a change, I kind of need to know where I'm coming from and where I'm going to. And so often it's hard to actually, like whether it's print statements or something, I always feel like I have to like to see it to understand it.
Yeah. Other way to do that is to add print k, but I find it super slow. Like, add print k, recompile, reboot the VM or your machine, try again, etc. So, and it would be stupid to keep doing that, considering what powers eBPF give you today. So,
yeah, love it. Well, audience, I hope that y'all learned something. I know that I learned a ton. So thank you for joining us here on episode 28. And if you have any questions, just give us a shout out on Twitter or jump into the Cilium Slack. You can go to slack.ebpf.io or slack.cilium.io, and we're in there. So yeah, thank you for joining us, and thank you very much, Martynas, for joining me. And I hope you have a wonderful weekend.
Yeah, pleasure. Yeah, if you have like questions on this tool, feel free to ping us on Cilium's eBPF channel. Happy to answer.
Awesome. Well, enjoy the snow, enjoy the weather. I don't know if you're going to get enough snow to get out there and have fun in it, but one way or the other, enjoy it.
Yeah, you too.
All right.
Thanks, guys.
Thank you, everybody.
Bye.
Bye. Hold on one second. There it is. All right. Bye.